Hello, I'm Bill Fitzgerald, CEO of Ziegler Capital Management. More than that, I'm an investment manager and a father. So when I consider the future, particularly beyond my lifetime, I actively engage in doing what I can with what I have to secure a sustainable future for generations to come. To that end, we've created a freestanding YouTube channel, Thick Sustainable Infrastructure Finance, as a quick and accessible tool to facilitate education and discussion about our common global environmental challenges and our specific efforts to rise to the ultimate environmental challenge. Thoughtful consideration over decades has led us to focus on financing thick, sustainable infrastructure. The following excerpt is one that we hope will help to broaden the conversation or clarify a particular dimension of our work. We hope that you will find it to be worth not only your time, but your further consideration as we all navigate these challenging environmental times together. We hope you decide to engage in the discussion by subscribing to the channel and offering your thoughts on specific episodes. We always learn from our colleagues. Thanks for tuning in, and here's our latest special episode.
What I would like to do in my few minutes here is just to lay the groundwork of the basics about climate change. And the fundamental basics from my point of view is that whether an object warms or cools is related to its energy gains and losses. If it gains more energy than it loses, then it's going to warm up. And those gains and losses are relative to its environment. So for Earth, our environment is space. So our energy gains from space are driven by our energy gains from the sun. And the energy losses we have is that any object that has a temperature emits radiation. And in this case, we call it terrestrial radiation or long wave radiation. And so the fundamental look at how the Earth's surface temperature, what it is, what its distribution is primarily determined by this balance between the absorption and emission of radiation. And if we look at it as a planet, what we see, and we can measure this from space because we have satellites. Wisconsin is the mecca of satellite meteorology. What we find is that the tropical regions are gaining more energy than they're emitting to space. And the polar regions are emitting more energy to space than they're gaining from the sun, which is not surprising because in the wintertime, they're in darkness. So the response to that is that the atmosphere and the oceans establish circulation patterns that are always trying to move energy out of the tropics into the polar regions. Now, what's happening with climate change recently is that our human activities are changing the composition of the atmosphere, and that's changing and modifying how we absorb and emit radiation. These gases, which are known as greenhouse gases, in particular are carbon dioxide and methane. These gases do not absorb solar radiation. So when we put them into the atmosphere, that solar energy still finds its way right down to the surface, doesn't have an impact on the energy balance of the planet, of the atmosphere. Surface heats up, emits terrestrial radiation. Carbon dioxide, methane absorb in that terrestrial radiation, and that causes a warming of the planet, of the atmosphere, and then the planet. So that's the fundamental basics as I see what happens about climate change. It's driven by energy gains, energy losses, and those imbalances. Now, even with that simple conceptual framework, we can start predicting what we might expect to see in a changing climate where the atmosphere is warming because we're adding these greenhouse gases. And so if you go to the next slide, here are some of the 10 things that we could relatively argue we would expect to see. One is on the right-hand side there, the temperature of the atmosphere is going up because we're increasing the amount of these greenhouse gases. As the atmosphere warms up, it's going to emit terrestrial radiation back down to the surface. It's going to be in contact with the surface, and that's going to tend to warm the surface. So might expect that snow cover, ice cover is going to decrease because of the warmer atmospheric temperatures. And we're seeing that. We're seeing Arctic sea ice decrease. We're seeing the number of glaciers decrease. And we're seeing also the amount of snowfall decreasing. Because the atmosphere is warming, its interactions with the ocean, we might also expect that the sea surface temperature would go up. Ocean temperatures will go up. And indeed, we're seeing that as well. And as you warm water, you're going to expect it to expand. As you melt glaciers and they find that water finds its way into the oceans, we might expect to see global sea level rises. And indeed, we're seeing that as well. And then finally, one thing that it's hard to argue in terms of the energy imbalance, but as the atmosphere warms up, we're going to see more water molecules in the atmosphere. So we would see an increase in the amount of humidity in the atmosphere. So those are 10 things that we would expect to see just to argue on the basic physics of a warming atmosphere. And all of these things are actually observable in today's world. Now, I'm not going to go through all 10 of these, but I want to give a couple of examples and then talk about how that impacts our lives. So the first one I want to show is our record of lake ice on Lake Mendota, and that's in the next slide. This is a long-term record going back to the 1800s. And so on the x-axis is the year, and on the y-axis is the duration of ice on Lake Mendota. Black line is the for a particular year. There's always a lot of annual year-to-year variations. And so we often will run a 5-year filter on that to smooth the data a little bit so that visually we can see what that impact is. Statistically, it doesn't have an impact if we were to run it on the black data. But if you look at the red line, you can see that there's a general decrease in the amount of time there is ice on Lake Mendota. And indeed, if you look at the last 20 years, so going back to about 2000, that thin straight line is the median over this 100 and something year period. And all of the last 20, except for 1 year, the duration of ice on Lake Mendota is less than that median value over the entire record. And if you go back to the beginning of that record, the first 20 years, you can see almost all of those years, they're above what that median value is averaged over the entire record of time. And if you look at those values, you can see that we're talking about between the last 20 years and the first 20 years, roughly 20 to 30 less days in which there is ice on Lake Mendota. So that's certainly reflective of a warming climate. And it also now impacts how we live. Right? A big thing in the Wisconsin culture is ice fishing. Many families do that. And if the amount of ice is changing on the lake, then it's going to reduce the amount of time that we can participate in that activity of ice fishing. If we go to the next slide, we can also look at some other aspects that we've looked at with regard to winter and springtime. One thing that we've looked at is the Wiki initiative analyzed surface temperatures during springtime and also looked at the springtime minimum temperature and how that's changed in the last 57 years or so. The springtime minimum temperature is going to be often reflected of what the nighttime low temperature is on average. And those red areas, you can see the springtime minimum temperature over the last 57 years or so has increased by about 1 degree. And the dark regions are almost 2 degrees. So what we're seeing, and we can do the same thing during the daytime for the springtime maximum temperature. And when we do that, what we see is that the nighttime low temperatures are warming faster than what the daytime highs are. We're also seeing that the greatest amount of warming is occurring in the wintertime and in the springtime. There are a number of ways to look at how the winter times are changing. That's one way. Another way we can look at it is how many times a year or days in a year is the minimum temperature less than 0 degrees Fahrenheit, so sub-zero temperatures. What we see now in comparison to over the 50-year record is that that is occurring less frequently, on the range of 6 to 24 days, fewer days in which the temperature is getting below 0 degrees Fahrenheit. So fundamentally, what we're seeing is we're still having wintertime. It's not as cold. Now, if you don't like cold winters, you may view that as a good thing. But if you like ice fishing, if you like snowing, those warmer temperatures are going to all influence how we do our wintertime activities. In addition, wintertime activities are really big for the Wisconsin economy. The other thing we can look at is how many days a year, or in the springtime, when do we have our first temperature or our last temperature less than 32 degrees Fahrenheit? And then in the fall, when do we have our first temperature less than 32 degrees Fahrenheit? And that time difference essentially defines the growing season for that year. And when we average that over the 50-year period, what we find in terms of trends is that the growing season is lengthening, anywhere from 1 to 4 weeks since the 1950s. And again, that'll depend on where you live in Wisconsin. Now, if you're a gardener, you may think, well, that's a great thing. But with that warming temperature and increased growing season comes invasive species as well. They can survive the harsher winters that we used to have 50 years ago. Those temperatures also affect cultural activities that we have. A big one in Wisconsin, as well as economy, not just culture, is maple syrup harvesting. Maple syrup harvesting, that's a good time when you have warm, sunny daytimes, and nighttimes you want cooler temperatures. And if our nighttime temperatures are increasing, that's going to impact the duration of the maple syrup harvesting time period. And in fact, predictions are looking out, by the time we get out to 2050, this is not going to be an optimum environment for maple trees to grow. They're going to be different trees that are going to want to be living in our climate. So I want to summarize it in the next slide by just saying, the physics in this climate change is very well known. We've known what the physics is for a long time. We observed this global warming. Experts agree that it's humans caused. I very much simplified things. These interactions are complex, but the interactions and the expectations are observable and they're consistent with one another. And then finally, I just want to mention that the way we have lived in terms of increasing carbon dioxide emissions into the atmosphere has changed our climate. And what we're seeing now is that changing climate is impacting how we live, not just in terms of energy consumption, but in what we do, how we enjoy outdoor activities.